find the area under the curve of y equals x squared between 0 and 2. And obviously there's a curve there, so it's not a circle, and that's really the only thing that we know the area of that's curvy. You know, I'm sure in geometry you develop formulas for areas of trapezoids, and Hero's and Brahmagupta's formula for area of triangles, or Brahmagupta's, I guess, for inscribed quadrilaterals. But anyway, you have all these different formulas, but we don't have ways of finding areas underneath things that are curvy, like I said, unless they're a circle. So what we're going to do first is we know shapes like rectangles. The area is very simple for a rectangle. So we're going to approximate the area under this curve by building rectangles such that the right part of the rectangle, the upper right corner of the rectangle, rests exactly at the level of the function for any given x value. So you can see how the right side of these rectangles is the exact height of the function at that specific spot. And then left-handed rectangles will have the left side of them at the height of the rectangle, at the height of the function at that specific x value. And you may notice that this particular left-handed rectangle situation has what we can call a rectangle down here. There's nothing there because the function has a height of 0 at 0, right? 0 squared is 0. So that first rectangle has no area. And what we're going to do is we're going to add up the areas of all those rectangles, and we're going to say, well, this is a pretty good approximation of what the area under that curve is. Of course, it's not going to be exact. So to do that, we actually have to measure the length, or the base and the height of each of these rectangles. So in this particular situation, I have 1, 2, 3, 4, 5, 6 rectangles, but we're going to pretend that there are n of them there. So the first thing is, what is the base of each one of these rectangles if there are n of them there? So now I want you to probably pause and think about what's the base of each rectangle given that there are n in this space. Okay, hopefully you've had a good thought about that. The base of the rectangle is going to be 2 over n, because the whole width of the thing is 2 and there are n rectangles fitting in here. In the case that I've drawn, it's actually 2 over 6, or 1/3 would be the width of each rectangle. You can clearly see a third, a third, a third, and you get to the 1. The height is obviously changing. So for the height of the first, well, if we just try to add up the areas, it'll look like the following. Base times, now we need a height, right? So this is going to be our height value of our first rectangle. Well, the height is actually determined by that circle. Well, maybe I'll put it in red so that it's real clear. The height of the first rectangle is whatever the y value is of that red dot. Well, the y value of that red dot, that's f of a little bit over from 0. And now how much over from 0? Well, that much over from 0. 2 over n over from 0. And we've multiplied these two things together because base 2 over n, height, is f of 2 over n. Now the next rectangle, its base is 2 over n. All of the bases will be 2 over n. That's f. Times f of, now we have to decide what is the x value here, or the height there, I should say, the y value. Well, it's f of something, and that something has to be whatever this x value is that I'm pointing at. Well, this one was 2 over n, and we need to go over 2 over n more, so now it'll be 4 over n. And that process will continue until we get to our last rectangle, where it'll be base 2 over n, height, that x value, that y value associated with the furthest out x value, which is 2, but we could represent 2 as 2n over n. You don't have to think about that. You couldn't just think about it as the base times the height would be f of 2, but I've written it as 2 over n so that or 2n over n so that I can see a pattern develop here. Now, my goal is to take that and rephrase it in sigma notation. So give yourself a try at that. Start with I equals 1, and, well, you go from there. Hit pause and give it a try. Hopefully you've tried it, and you should have I equals 1 to n, because we're adding up n rectangles areas. Remember, the overall goal here is to find the area of each of these rectangles, add them all up, and say, well, this isn't the exact area under the curve of x squared, but it's pretty close. So, I equals 1 to n, you can clearly see every time we have 2 over n as our base. And that does not depend on what rectangle you're at. Every single one of them has a base of 2 over n. And now, it's f of 2 over n, 4 over n, 2n over n. It's actually f of 2i over n. If you're wondering where the I came from, well, the I is the indexed variable that I have in my sigma notation. So the first one, for example, if I was 1, it would be 2 over n times f of 2 times 1 over n. That's 2 over n. That's that one. If I was 2, it'll be 2 over n times f of 2 times 2 over n. That's 4 over n. The next one would be 2 over n times f of 6 over n. So the I variable gets us all these terms, and if you do 2 times n over n for the last term, you'd get this one. So now we're going to work with that instead of that. Okay, so the first thing I'm going to do is pull the 2 over n out. And secondly, f of 2i over n, think about what the function is. The function is x squared, right? So it's that thing squared. So it'll be 2i over n squared. Okay, and now I need to free up some space. So I'll have 2 over n. This will become 4i squared over n squared. And now I'm going to resume my work down here. So that'll be 2 over, actually, let's make it 8. That's a terrible 8. 8 over, I got 8 because 2 times 4, bring those together. N times n squared, that's n cubed. And again, not a great n. Of I squared. And this is one of those 4 formulas that we learned in the last lesson. It's on the PDF as well. But it is n times n plus 1 times 2n plus 1 over 6. So you get 8 and n plus 1, 2n plus 1 over 6. And now I'm going to leave it to you to verify that that is 8 over 3 plus 4 over n plus 4 over 3n squared. I'm just going to make sure the camera can see that. Right, so just so that you can check your work there. Okay, what this means is that if I plug in an n, for example, 100, if I want to know the area under this curve, if I were to have stuffed 100 little rectangles under here, it'll be 8/3 plus 4 over 100 times 4 over 30,000. If you add those numbers up, it'll tell you the area of all the 100 rectangles under here. What we have to keep in mind is that this number is actually larger than the actual area under the curve. Okay, now we're going to pursue the left hand. The left hand is going to be a little bit more complicated because, well, you'll see. So the terms here, well, first of all, the 2 over n is easy, I think, for all of us to see. 2 over n plus this one right here, the leftmost rectangle, actually is f of 0. I don't mean plus. then it's 2 over n more times f of whatever that is, but it's over by 2 over n. And you might think, well, this is really no big deal, and then you just keep going. 2 over n times f of 4 over n, and then you get to your last one, but the last one is 2 over n times, not f of 2 now, it's that one right there. It's f of 2 minus, or 2 times your, it's back 1, so 2 minus 2 over n. It's f of that, which is 2n over n minus 2 over n. So it's 2n minus 2 over n, so I'm going to write it as 2n minus 1 over n. Okay, so now, and again, that is the x value right there of that red dot. Now we're going to write this in sigma notation. So, in sigma notation, that's 2 over n. Well, I is going to go from 1 to n because we want n rectangles. And then the hard part is this. It's f of 2i minus 1 over n. Just verify that for yourself. But when I is 1, I minus 1 will be 0, so that'll be f of 0. When I is 2, 2 minus 1, that's 2 times 1 over n. There's our f of 2 over n. When I is n, it's 2 times n minus 1 over n. So you might have to go back and think about how I got this x value right here, f of that, and then reconcile it with that formula. Now I'm going to do the same thing I did before, which is to pull out the 2 over n. And then f of that stuff, that'll be all that stuff squared. Okay, so I'm going to get rid of this work. Why is it f of that stuff squared? Because that's what the function said to do. So it's all of that squared. And now that's going to be a 4, that's going to be an n squared. So we end up with 8 over n cubed outside again. And you, oh, sorry, I put my squared in the wrong spot. The squared should be out here. I don't know why I had an extra one there. 2 squared is 4, n squared is n. Suck those out. And then you have I minus 1 squared. Problem here is, you're going to have I equals 1 to n of I squared minus 2i plus 1. Now each of these has a separate formula associated with it. Remember, the I squared one is n times n plus 1 times 2n plus 1 over 6. The I one is n times n plus 1 over 2, and then this would just be 1n. I'll leave it to you to verify, after a whole lot of work, that this one is equal to the same thing as before, but minus 4 over n plus 4 over 3n squared. So the only difference is that sign right there. I'm just going to do a time check. Okay. Now, if you look at the two of these things, the interesting thing about them is they're the same thing, but now let's take the limit as n approaches infinity of both of these things. And what do you get? Well, 8/3 minus 0 or plus 0, 8/3 plus 0 plus 0, which tells me that the area under this curve must be exactly 8/3, because this one's larger and this one's smaller. So the point there is we over approximated here, we under approximated here, and we found that in both cases that these things converged to 8/3, which means we found the exact area underneath this curve, albeit with a very long thought process. You might have to think about this limit, and if you're wondering, why did we take a limit? Well, I'm thinking, if these rectangles, you can see there's some empty space here, but the way to make that empty space go away is to make really, really, really thin rectangles, and then do the same thing over here with all that extra space, making thin rectangles, and then, well, there you have it. You'll have a slightly under-approximated version, a slightly over-approximated version, and they will converge at 8/3 when you have an infinite number of rectangles.